Okay. First of all, I want to thank the Tohoku Forum for Creativity and the organizers, especially Shigeru Sakaguchi, for their kind invitation to give one of the courses in this workshop. And this is my third time in Sendai, and I always enjoy all my visits. So thanks a lot for this third opportunity to come here. Okay, so the title of the course is Topology of Nodal Sets of Solutions of Elliptic PDEs. Of course, please interrupt me if you have some questions, comments, or want me to give more details. No problem at all. Okay. So the course will consist of 6 lectures in 4 sessions. You have seen already the program. It's 4 sessions of 1 hour 30 minutes. So in principle, what I would like to tell you, it's the following outline. So the first lecture, this will be just an introduction, general introduction to the problem. It's a panoramic view of the subject. So this will be quite informal. Just I will state a few problems and also some informal statements of theorems, of the theorems that I'll prove in the next lectures. So in the second lecture, and this will take less than 1 hour, maybe about 45 minutes, let's see. So in the second lecture, here I will introduce the general strategy that I will use to address many of the problems that I'll consider in the course, and 2 technical tools that are very important to approach these problems. So the title of this second lecture is General Strategy. And the 2 techniques that I'm going to introduce in full detail. Here is a theorem by Thom and a Runge type theorem. A Runge type global approximation theory. So this theorem by Thom is something which is well known in differential topology, but it's not been widely used in PDEs. So I'll introduce just a statement, not the proof, although it's not very hard. And I state a global approximation theorem for a very particular PDE, although the statement holds in a much broader context. And the original context for this is Runge. This refers to complex analysis. It's a generalization to elliptic PDEs of the classical Runge theorem of extension, well, not extension, of global approximation of holomorphic functions. You'll see what I mean in the lecture. And this second lecture will take some time. It's, I think, maybe 2 hours, because I want to prove in full detail this Runge theorem for a special PDE, for the Helmholtz equation, actually, which is the model equation that I'll study in these lectures. So in lecture 3, it's so up to now here in this second lecture, I'll not talk about nodal sets. It's just the introduction of 2 technical tools. In the third lecture, I will talk about nodal sets of solutions to the Helmholtz equation. So of Helmholtz in Euclidean space. Okay. And I will use these 2 theorems, Thom and Runge, and the generalization of Runge, to prove a realization theorem for the nodal set of entire solutions of Helmholtz in Euclidean space. And this Helmholtz equation, I will write it in a few minutes, it's the model equation in this lecture series. Everything, or almost everything I'm going to explain here holds in a much more general context for very general elliptic, not only elliptic, also parabolic PDEs. But since the ideas are essentially the same as in this model particular case, I will just focus on this particular situation, this particular equation. So this is, and here these two lectures, lecture 2 and lecture 3, I intend to provide detailed proofs of everything. So this would take probably 3 hours. So in the last 3 lectures, lecture 4, lecture 5, and lecture 6, this will be some applications, or non-trivial applications, I'd say, of these techniques and also of this result for the Helmholtz equation, for the nodal set of Helmholtz, into apparently unrelated context. So lecture 4, it's an application to the nodal set of some Schrödinger operators. And here again our model will be the quantum harmonic oscillator. The lecture 5 will be an application to nonlinear PDEs, and again I will focus on a model important PDE, which is a Lenkan. So I will talk about nodal sets of the Lenkan equation. And in the last lecture, I hope I have time to read it. I will talk about during the whole course, my space will be Euclidean space, Rn, so non-compact. And here in lecture 6, I want to say something about PDE in a compact space. And here I consider the simplest case, which is nodal sets of eigenfunctions, high frequency eigenfunctions. Of the Laplacian of the domes. So Euclidean space with periodic boundary conditions, flat domes. Okay? And here, probably in these 3 lectures, I think I not have time to give all the proofs, so just I'll state the main results here, and some ideas and hints on how to prove these things. Okay? So the precise and detailed proofs will be only for these 2 lectures, in the study of the nodal set of Helmholtz equation, and in the proof of the global approximation Runge-type theorem. Okay, so this is the outline of the course. So let's start with this first lecture, which is, as I said, a bit of hand waving, just introducing the problems and some informal statements of theorems. So this. So first lecture. So what's the kind of objects that I want to study here? So if you have a function, say a smooth function in Euclidean space, real valued, a way of visualizing this function is through its level sets. So given a function, let's call it U, smooth, say real valued from Rm to R, then we can visualize for a way to visualize it, it's through its level set. So by level sets, I just mean, so let's denote it this way, U minus 1 of C is the set of points in Euclidean space where the function takes the value C, the constant value C. Okay? And this defines, if you consider all the level sets of the function, this defines a partition of Euclidean space into some closed subsets. And in some cases, this partition is even a foliation, etc. But actually, I'll not study the whole partition, but just a very precise level set of this, which is the nodal set. It's a particular case of this when C equals 0, the zero level set. It's sometimes called the nodal set. And I will denote by n of u. This is simply defined as the set of points in Euclidean space where u takes the zero value. And among all the values of the function, this is quite important because, of course, it's invariant under rescalings of the function. If you multiply u by another non-vanishing function, say lambda, then the nodal set remains the same. This of course, doesn't happen for the other level sets. So in this sense, it's invariant under rescalings. And that's why it's important, among other reasons. So these objects here, these level sets, so why do we analyze, or why do we establish these objects? So they have a very clear physical interpretation. So one of the motivations comes from physics, which is a physical interpretation of these objects. So, and for example, in the case that U is the electrostatic potential, so for example, if U is the electrostatic potential, then these sets are nothing else than the equipotential surfaces of this potential. Okay? Equipotential. The equipotential surfaces. Or, for example, something similar appears in the study of Newtonian gravity. So, and in this context, it's interesting and sometimes quite useful to understand the shape of these equipotential surfaces, both for Newtonian gravity or for electrostatic potential. So you have a problem, which is to understand the shape. Shape of some physical objects that amount to study actually the level set or the zero set of some solution to a PDE. So the shape of conducting or self-gravitating in the case of Newtonian gravity. Self-gravitating surfaces in equilibrium. So this, the study of these objects, which is of interest in physics, this amounts to study the topology and geometry and geometry of the level sets, in particular the nodal sets. so this is what I mean by the shape of the surface. Its topological type, how many holes or even components, etc. It has, and geometry refers to the curvature, more precise geometric features of the surface. Okay. So this is a motivation to study these things. So there is a difficulty here, which is that usually the function that you want to study, this electrostatic potential or this Newtonian gravitational potential, is not any function. It's not a general function. It satisfies some PDE. Okay, so this is a question which has a constraint. Your function has a constraint. So usually, for example, in the electrostatic case, we have a constraint which is, say, the Laplace equation. The Laplacian of u is equal to 0 in Rn or in the complement of a domain, etc. Depends on the problem. There can be some mass here or some density, some charge density here, depends on the problem. Just let's think of the harmonic functions case, which is simpler. So this is a constraint on your function. Okay, so then it's not so easy to study the level sets of your function. For example, to understand which geometric features these level sets can have. For a general function, it's of course easy. Given any hypersurface, more generally, given any closed set in Euclidean space, there exists a smooth function which vanishes precisely at this closed set. So this realization issue is easy if there is no further constraint. But when there is a PDE involved, then things become much more complicated, because the solutions to the PDE is a very, very small set in the space of all smooth functions. It has infinite codimension, etc. So to understand the kind of problems that I'll address in this course, I'm going to focus now just a bit, a few minutes, in this case, the electrostatic case, and just pose very precise problems that we would like to solve in this context. So let's focus on this case to illustrate the problems. So to illustrate the problems we are interested in, let us consider the electrostatic potential. Or say, let us consider harmonic functions. Okay, so simply functions satisfying that the Laplacian of u is equal to 0 in the whole space, Euclidean space. Okay, and I want to understand, for example, which properties a regular component of the nodal set has. So let's focus on a regular connected component, regular connected component of the nodal set of n of u, the zero set. And regular, as usual, the regular set of a function is a set where the gradient doesn't vanish. So regular means that the gradient of u is different from 0 at any point. Any point. Okay. So the nodal set may be disconnected. It may have many components. Let's focus just on one component, one of these possibly infinitely many components, and just let's study just the components which are regular, the components for on which the gradient doesn't vanish. Okay. So in this case, if we want to study these objects, okay, there is a general fact. Which is that by the implicit function theorem, then it's not hard to prove that any regular connected component of n of u of the nodal set it's orientable, is unorientable, it's an orientable codimension 1 C infinity, actually analytic. Submanifold of Euclidean space without a boundary. Okay, this is a general fact for any connected component of a regular level set of a function, of a smooth function. Okay? Here there is no PD. We are not using any PD. Just you have to remember what you learned in your course on differential geometry or differential topology. So in this sense, we don't understand yet anything about the PDE, because the point is how the harmonicity is transmitted into the nodal set. That's the point. This is a general fact, but we want to understand more something that is precise, that it's specific for harmonic equation. So the point is how harmonicity which part refers to the PDE, how harmonicity is transmitted to the level sets or to the nodal set in particular. This is a question that we want to understand. So there's something easy, and this easy will be an exercise for the students. There are many here. So an exercise. Okay. Is that you can prove, it's not very hard, that each one of the connected components, it doesn't matter actually if it's regular or not, of the nodal set of a harmonic function is non-compact, cannot be compact. So let's prove that, well, this will be the exercise, I'm not going to prove it. So prove, please, that prove that each connected component, is non-compact. Okay. For this same nodal set. Okay, and just a hint is use maximal principle. So then with this result, you see that, okay, there is something, not very strong, where you see harmonicity of the function. Harmonicity is transmitted, in particular, in the fact that you can have compact components for the regular level set. For example, if you consider, say, this set, in Rn, which is compact, this is forbidden. This cannot be a component of a regular level set, of a harmonic function. Okay. So, okay, you have some instructions. the nodal set. Compactness is forbidden. But what else? Okay, this is a very weak property, being non-compact. So we would like to understand more. Okay, so among non-compact submanifolds, which are many, of course, which ones can be nodal set of harmonic function? So the precise question that one can try to solve is the following. So question is, does there exist a harmonic function in Euclidean space, such that its nodal set N of U has a component connected component diffeomorphic to a genus G torus with n ends. So this is the question, and the picture of the question, just to know what genus G and n ends means, is the following. So you have a torus. Okay, the standard torus is just this, like a ring. Okay, so this is genus 1. But, okay, since we consider genus G, this means that, of course, your torus may have more than one pole. So, for example, you have this picture. Okay, let's put 3 handles. Okay, so genus 3 in this case. And this ends, it's the number of cylinders that you attach to your surface. So let's say, for example, something like this. And put a third one here. Okay, so this is n equal to 3 ends. Okay, there's 3 ways to go to infinity. This is an end of a manifold. It's the complement. It's the number of connected components of the complement of any ball. So here, if you take any big ball, there will be 3 components in the complement, 3 cylinders. Okay. So the question is, does there exist, and this has no boundary. By this I mean that this goes to infinity. Okay. This is a embedded property in the Euclidean space. It has no boundary. So the question is, does there exist a harmonic function which has whose zero set has a component which is this object here? This is the problem in a more general context, not only 3, but genus G and n. That's the question. And even you can ask this question for more general objects. What about an infinite torus? For example, something like this. Infinite torus. repeat this on the left and on the right. Infinitely many genus. Genus is equal to infinity. So does this exist? Is this possible for a harmonic function to have a component of its nodal set of this with this shape? Okay, so this is the kind of questions that I'm going to address. Given a picture of a surface, here it's easy to draw the picture because we are in dimension 3. Actually, the course will be in Rn, so just think of any 5-dimensional manifold in R6. Then it's not it's not possible to draw it, of course, and it's not possible to classify it, of course. But we are interested in understanding which ones of these submanifolds of Euclidean space can be actually a level set or component of nodal set of a solution to a PDE. That's the question. So in the case, as I said, our model equation in this course is Helmholtz equation. I'm going to write it now in a couple of minutes. And why? Why is this our model? Okay, we have to choose a model. But we could have chosen as a model something that looks simpler, that is harmonic functions. It's Laplacian equal to 0. Okay, in this case, the work is done. We can understand the level sets. In particular, the answer to this question is affirmative. The answer to the question is affirmative. But it's much harder than what I'm going to explain here because of non-compactness. But the proof is hard. Because of non-compactness. Non-compactness of the nodal set. This was one of the exercises, the first one actually, that the nodal set, each component in the nodal set must be non-compact. So non-compactness, it's difficult to deal with because, well, on the one hand, I mentioned that in the second lecture I introduced two techniques, Thom's theorem and Runge-Tile theorem, global approximation. So non-compactness makes both theorems very hard to prove. In the case of Thom, this wasn't actually done. We had to prove a Thom's theorem for non-compact submanifolds, and it's complicated. And in the case of Runge, it's more complicated, a global approximation theorem for non-compact sets than for compact sets. So that's why in these lectures I'll not consider this case, the case of harmonic functions. So instead I will focus in another equation, our model equation. Our model equation will be Helmholtz. And Helmholtz equation, it's simply the Laplacian of u plus u equal to 0 in Euclidean space. The solutions to these equations are sometimes called monochromatic waves. Monochromatic waves. And the reason to consider this equation is that it allows compact components for the level set. So here, since solutions to this oscillate, there is no maximum because this has sign, so there is no maximum principle for this. You can have indeed compact level sets. Okay. And we will study the compact components of the level set, or of the nodal set in particular. It may have also no compact components that you can study actually, but I'll focus just on the compact ones. Okay. So this is our model equation. This is the equation that I'll study during this course. So now, in order to finish this first panoramic lecture, I want to state informally the kind of results that I'll present in the following lectures. So in the third lecture, I said that I'm going to study nodal sets of Helmholtz equations, of solutions to Helmholtz. So the statement of the theorem that I proved in the third lecture is following. So in lecture 3, I will prove the following. So the theorem, this is just an informal statement because I'm not going to define everything now, just to have a picture of the kind of theorem that we will state precisely in this lecture. So the theorem, the formal statement, is the following, is that any, so it's just the answer to this question, but for compacts and manifolds. So for compact, just think an example is just thinking of this genus 3 torus, but without these 3 cylinders. Just simply, for example, something like this. The genus 3 torus, compact. Okay. So the theorem says that any compact submanifold of the Euclidean space is a component of the nodal set up to a diffeomorphism of a solution to Helmholtz. Okay, not any solution, actually that decays at infinity, but okay, I'll explain some properties of this solution. It's a special class of solutions of Helmholtz, which are called Helmholtz solutions, but I'll explain it later. And so here in this statement, so what this says is that given any compact hypersurface, no boundary, orientable, of course, smooth, in Euclidean space, so this particular instance, in higher dimensions you cannot even draw it, but it makes sense, the object, of course. Then we say that there exists a solution to the Helmholtz equation, Laplacian of u plus u equals 0. Defined on the whole Euclidean space, of course, is a global solution, such that if you look at the nodal set of the solution, the 0 set, and if you look at a component of this nodal set, then there is one of these components which is diffeomorphic to this object. And here, diffeomorphic, this means, to diffeomorphism, this means that there exists a deformation. So I don't want to write in a precise way now because I'll do it in the third lecture, but essentially is that there is a deformation, a continuous deformation, of space which puts this into the nodal component, and vice versa. Okay, into and onto. Actually, it's a different. Okay, so you can move this in a continuous way without self-intersections, without any development of singularities, etc., so that you get, or it reaches in finite time exactly the nodal component that you want. That's the theorem. So this is the theorem that I'll prove in the third lecture. Probably this will take 1 hour after the proof of the technical lemmas in the second lecture. So in the proof of this, it will be important what I will introduce in lecture 2. So in lecture 2, the main tools to prove this theorem, this result, will be introduced. This is in the second lecture. So, and then I said that in the last 3 lectures, 4, 5, 6, I will apply this this theorem to 3 contexts, different contexts, not trivial application, because the proof of these 3 results will require also new ideas. But it's you can see as an application. So in lecture 4, what I will do is to show that the nodal lines of complex valued eigenfunctions I will study nodal lines of complex valued eigenfunctions of this Schrödinger operator, which is the quantum harmonic oscillator. Dimension 3. Okay, this x, this is just modulus of x is just the distance from point x to the origin. Okay, so this is the classical potential of the harmonic oscillator, the quadratic potential, usual quadratic potential for harmonic oscillator. This defines a perfectly well-defined eigenvalue problem in H2. Okay, so this has eigenfunctions which are square integrable. Actually, you can write them explicitly using Laguerre polynomials, Gaussian functions, etc. And the point is that we show proof that, and here this is complex valued, so this belongs to H2 of R3 to C. So if you want to study the nodal set of this, okay, it's H2, but of course it's infinity by regularity. So if you want to study the zero set of this is the zero set of a complex valued function. So the zero set, the intersection of zero set of real part and imaginary part. Real part and imaginary part. Typically this is lines, it's the intersection of surfaces. So that's why I say, I talk about nodal lines. So it's just intersection of surfaces. Just the intersection of 2 surfaces. So what I will prove is that the node types of nodal lines is any node type is realized. Node type. And this by node, okay, I explain what a node is. A node is a curve, it's a closed curve in space. It could be a node can be a simple curve like this, or it can be a straight coil, or it can be many things. But so the theory will say that any curve, any closed curve, arises as the intersection also of real and imaginary part of eigenfunctions to this problem. L2 eigenfunctions. So here you have a precise control on the space where your solutions live. We are L2 solutions, okay? For the Helmholtz equation, for example, there are no L2 solutions. Okay? This in lecture 4. In lecture 5, this is just to have a global picture of the things that I'm going to study here. I'm going to present. In lecture 5, I'm going to study again nodal sets. But in this case of the Alenkang equation. Which is this. It's like Helmholtz, but with this cubic term here. The operation of u plus u minus u cubic, u cubed is equal to 0. And I'll prove, say, an analogous theorem to this one. Any compact topology can be realized. By bounded solutions. Because usually in Alenkang problems you study bounded solutions. These are bounded solutions. Well, they don't have this finite index in some sense. Or in other words, this of course doesn't contradict the George's conjecture and all this stuff on the level sets of Alenkang, because these solutions are not monotonic in one direction, etc. But they are still bounded solutions. Actually, they decay a bit. So this will be lecture 5. And in the last lecture, lecture 6, I will study nodal sets of eigenfunctions on the torus. And again, I will prove. Well, here I think I'll not have time to prove, just to state and say a few ideas about proof. About this problem. I will consider this problem. The Laplacian of u minus lambda u in the torus. Okay. And I will show that, again, an analogous result. Any compact topology can be realized for high enough frequency. So if lambda is high enough, this is high enough, then any topology can be realized. Then something like this. Okay. In the torus, which is where your functions live, in the torus. And here it's important to have high eigenvalues. So you know this. You know the eigenvalues of this. This is just simply k squared, where k is a point in the lattice. So you know any eigenvalues of this form. The multiplicity grows quite a lot when the eigenvalue grows. Multiplicity grows with the eigenvalue. So you have so the dimension of your eigenfunction space is very large. The dimension of the eigenfunction space is very large when k is large. So then you have a lot of functions to play with, and that's why you can prove this realization result. Okay. But we'll see. Okay, and this finishes this the first lecture. So now it's time for questions. You have to, because after this I will start with the second lecture. These two technical tools that are important. Stop and Google. The question, so you can see the general picture and the kind of problems that I want to study. Yeah, very strange problems for an analyst. Yeah. A magic for an analyst, they say, or PD analysts say that how is this possible? But it is. Okay. So one of the funny features of these problems, apart from possible interest in applications, this I don't know, is that to prove then, so the proof of this result requires a combination of different ideas coming from different parts in mathematics. So the question is actually a question that a geometer or a topologist could ask. Okay, it's a question about an object that lives in the world of geometry, or even topology. It's the zero set of a function, and you want to study its what is called the isotropy type. So this concept of isotropy type, the shape in this sense, is something that comes from topology. But the point is that here you're asking this question not in a geometric framework or in the world of topology, but in the world of PDEs, of the analysis of PDEs. So the world of the differential topology and of the analysis of PDEs don't talk too much to each other. The kind of techniques are quite different. The kind of problems in general are also quite different. The usual very fine estimates in the analysis of PDEs is in general not enough or not well suited to the analysis of these more global questions. And conversely, the analysis of topology in other contexts as foliation theory, etc., using what is called H principle or other kind of techniques, doesn't fit well within most of PDEs. There is an H principle for some kind of PDEs, but which is actually totally different to what geometers call H principle in some topological context. Okay? So this is one of the funny features that you have to combine ideas from both worlds. And actually, finally, the combination is not so hard. The proofs are not so hard. Okay, so let's see if there are no questions. We can start with the second lecture.
One question.
Yeah.
In lecture 5,
yeah.
you deal with
nonlinear
equation.
Right.
Other equation is all linear.
Yes, right.
So then, so you need some difference.
You need some difference, an extra, yes, because as I said, this, well, I will explain that this global approximation theorem only works for linear PDEs. Here you can do it for nonlinear because we consider solutions set in the linear regime, solutions which bifurcate, say, from a solution to the Helmholtz equation. So in the case that this term U is very small, this can be done. And the application of these techniques and of these ideas to the nonlinear world is always in the same way. You can apply to other PDEs, not only these, also to the harmonic, to the zero mean curvature hypersurfaces and to other elliptic nonlinear PDEs, but it always goes in the same way. It's just as bifurcation or perturbation, probably is the best word, from a solution to the linearization, to the linear PDE. But in general, it's a linear technique. You'll see in the proof now in a second. Okay, so in the second lecture, and it's more than only for linear. It works pretty well for linear and for non-compact spaces, non-compact also. Because this Runge type global approximation theorem only works for non-compact, I'll say why. So this lecture 6, where we consider compact space, also requires another idea. That's why here I write high frequency, because it's another idea. It's combined with the previous one. Okay, so second lecture. It's so as I said in this lecture and in the third lecture, I focus on monochromatic waves, just Helmholtz equation. So let's write it again. Expression u plus u equals 0 in Euclidean space. Okay. And the question is what I already mentioned: how flexible or rigid are the nodal sets regarding their topology? How much topology you can have in the nodal set? Okay. So we have this question. now more precisely defined as before. And this will set some notation for the next lectures. So let sigma be a compact hypersurface in Euclidean space. Okay. And by hypersurface, this is the definition that I consider in these lectures. Always that I talk about hypersurface, it means the following. It's a codimension 1, C infinity, submanifold, orientable, and without boundary. Okay. This will be hypersurface in these lectures. Okay, no boundary, orientability, submanifold, so it's embedded, and smooth enough, infinity, or actually it will be analytic in general, and codimension 1. Okay, so we have a sigma of this type, which is compact. Then the question is, does there exist a solution U to the equation, to the Helmholtz equation in Rn, so global solution, and a diffeomorphism I from Rn to itself, such that the image of sigma under the diffeom, the deformation of sigma under the diffeom, is a connected component of the nodal set of U. This is our question during these two lectures, lecture 2 and lecture 3. And I'll answer it in lecture 3. Proving actually that indeed anything can be the component of nodal set. Okay. So there are two remarks that are important. So first remark concerning this question. Okay, and diffeom, well, simply I recall the diffeom is a map from Rn to Rn. It will be smooth. In all our diffeoms will be smooth. Okay, it's a map from Rn to Rn, smooth. It can be inverted. It has inverse, and the inverse is also smooth. That's in particular, it's an injective map. Okay, but it's a diffeom in the standard way, standard definition. So a first remark is that we want solutions that are global. The problem is difficult because we demand our solutions to be global. For local solutions, this is easy, and let me show you why. So key point is global solution. So for local, meaning solutions not defined on the whole space. For local, this is it. So let me show you why. So we have sigma. So let's put this picture of sigma. Submanifold, no boundary, orientable, compact. So let's see compact deformed sphere. Okay, in Rn. Has dimension n minus 1. It's called dimension 1. So of course, since our statement will be always a statement which involves a diffusion of physics. We are free to deform our hypersurface as we want, in case it helps. Okay. So let's deform this to make it analytic. So we deform and we can assume that sigma is a real analytic hypersurface. It's the zeros of a real analytic function. This is always possible by Whitney theorem, by density of analytic in smooth, the CK topology. You can always do this. You can always deform a hypersurface to make it analytic. Small deformation, close to the negative. Okay. So let's do it. Now let's consider the following problem. So in a neighborhood of your surface, you can consider this this construction. So a function which solves Helmholtz in this neighborhood, n of sigma is a neighborhood of sigma. Neighborhood of sigma. Thin enough, but not yet set, and such that V is equal to 0 on sigma, and the normal derivative. So if you take, say, one of the orientations, for example, this one, the normal unit normal vector. This exists globally because it's orientable. So unit normal vector. So just take that the normal derivative is equal to 1 on sigma. Just take this problem. Okay, you know this has a solution in a narrow enough neighborhood. This is Cauchy-Kowalewski theorem. Okay, so by Cauchy-Kowalewski, you have a solution to this problem, a function V that solves Helmholtz equation in some neighborhood of your surface, sigma. Okay, it's a neighborhood of your surface, and actually that vanishes on the surface, and only vanishes there, in fact, because you have prescribed the normal value to be 1. So for this narrow neighborhood, since the gradient is not vanishing, in the narrow neighborhood there are no other components of the zero set. So actually this solves this problem. This is a solution to the Helmholtz equation, which has a nodal set, not only a component, but the whole nodal set is given by sigma. Okay? The only DPO here maybe is just to transform your smooth surface onto an analytic surface, because you want to use an analytic theorem, you want to use Cauchy-Kowalewski. Okay. So, in this sense, I mean that it is easy. The problem is that we want solutions defined in the whole Euclidean space. So, if you have this solution defined in this neighborhood, it remains to extend it here and here, in case extension is possible. It's not possible. Of course, as we know, a local solution is not the restriction of a global solution. In a very, very general, in a quite general context. Okay? So the idea that we'll consider is not to extend, but to approximate. The question will be: is any local solution the approximation of a global solution in your compact set? That there exists a global solution that is very close with respect to some norm to this V in the compact set. That's what I will study in this second lecture. And actually, in this particular picture that I draw here, this global approximation is not possible. But so we have to do it in a different way. But that's the idea. So this is a first remark. Local is easy, global is difficult here. A second remark is about this diffeomorphism. So is it necessary, the diffeom? That's the question. Oops. That's fine. Oh, probably later it will be fixed. So a second remark is about how important the diffeom is. If you have questions, of course, please interrupt me. So, second remark. Second remark. It's why a realization result about up to diffeom. Okay, so the thing is, maybe it's true, this statement, if we just drop this diffeomorphism. Maybe it's true that given any hypersurface, there exists a global solution which vanishes exactly from this side. Is this true or not? But we know some abstractions already for the case of harmonic functions. This is a nice result. So, for example, let's consider, so there are abstractions. Without the diffeom, there are abstractions. And for example, consider in the plane, in R2, Euclidean coordinates, x1, x2. Let's consider this family of curves. So x2 is equal to x1 to the power n. No, not n. K. Okay? And k bigger or equal than 1 is an integer. Okay? This family. So you have a linear curve, you have parabola for k equal to, you have the cubic, etc. So the point is that these curves can be a component of the nodal set of a harmonic function if and only if k is equal to 1 or 2. So all of these curves are diffeomorphic, of course. All these curves are diffeom. They are diffeomorphic to the straight line. Okay, you can form all of them to be a straight line. They are all open. Okay, but they can be a component of the nodal set of U for a harmonic function U, for U solving Laplacian of U equals 0 in R2, if and only if k is equal to 1 or 2. Only in these two cases. So for k equal 1, you have this line. Of course, it's easy to construct the harmonic U which vanishes on the line. It's easy, so it's not an exercise for the student. The second one is an exercise because it's not so easy. So for k equal 2, this is k equal 1. K equal 2, you have the parabola. Okay. This is again the zero set of some harmonic function. But this is not a polynomial. Harmonic function for which this is the zero set is not a polynomial. So exercise. Which U has a component of the zero set actually. It has many other components. Vanishes on more curves. Infinitely many more. So this is yes. It's a transcendent function, not a polynomial. And for the rest, k bigger or equal than 3, U does not exist. Vanishing exactly on this curve. Of course, if you deform it, if you deform the curves, it exists. But without deformation, without diffeomorphism, this doesn't exist. The exercise is only this, not to prove this. This is much harder than the example. This is a paper, and I don't remember the reference, but if you're interested, it's a paper from the 60s, classical resolving harmonic function theory, by several people, Shapiro. I don't know exactly. There are several Shapiros, and also probably it's three authors of Plato, Shapiro. Okay, but don't look at the paper because the example is there. So first, before looking at the paper, try to construct the function by yourself. Okay. So these are the two remarks that I wanted to tell you. So when shall we finish? Maybe at 2:30? 2:40. Okay, so now I want to tell you how we can address this problem. We want to solve this question, and the strategy. One could think of other strategies to prove this, but the only one that we know at this moment is the following. So the strategy. To address the question, to answer the question, a general strategy. Actually, this is quite general. It works for many PDEs, not only the Helmholtz. The main properties of the PDE is that it must be elliptic or parabolic. It doesn't matter. It must be linear. If you are in the nonlinear, if you consider nonlinear equations, okay, it must be close to a linear one, and in a non-compact space. Okay. But apart from this, it's quite general. You can apply this to the Euler equation, in fluid mechanics, Navier-Stokes equations. So not only in the setting of in this say geometry of elliptic PDE setting. So the strategy consists of two steps, roughly speaking, quite general steps. So the first one is indeed the construction of a local solution. You need something to start with, and the good starting point is local solution. So we construct a local V. A local solution, solution V. Solution V. And the equation translation of V plus V equals 0 in say n of sigma, a neighborhood of sigma. Such that you want that this local solution has a zero set just given by sigma. So such that B minus 1 of 0 is precisely sigma. Okay? So first we want to construct this. How do you do this? You can use Cauchy-Kowalewski, for example. Cauchy-Kowalewski as before. But sometimes Cauchy-Kowalewski is not good because of the second step, I'll tell you why. And for example, for this particular case of this, for this question, the Cauchy-Kowalewski is not good. So you need to consider an appropriate boundary value problem. And you can think even other techniques to construct a local solution controlling the zero set. It doesn't matter. So this is the first step. The second step is the globalization. So you have your solution defined in the neighborhood. You want a global solution. How you globalize? Extension is not possible, so it's approximation. So we approximate V by a global solution defined on the whole space. Okay. Satisfying global solutions, of course, satisfies Helmholtz equation. And approximation is in CK norm, usually. CK norm. So this meaning the difference, if you measure the difference of U and V in this neighborhood, this will be small enough. And this K will depend on the problem. Usually K, sometimes here, for example, K equal 1 is good. For fluid mechanics, for some reasons, you need K equal 4. It depends on several things, the number of derivatives that you have to control. Here, K equal 1 is okay. But you need this norm. Okay, just an approximation in a very weak sense, L2 or whatever. It depends because, well, generally what you do is that since your solution, since your object satisfies and these elliptic PDEs, you can easily promote L2 norm or L infinity norm or whatever to higher norms. But it will depend on the problem. Here it will be easy, in fact, because the equation is easy. So this is the second step. But there is something that one has to control here, and it's the following. It's, so you have constructed your local solution with your zero set, and now you have a global solution that is close to the local one, a good norm. But you want to look at the zero set of the global solution, not of the local solution. So the point is, does the global solution have a zero set close to the zero set? And close not only that is in the neighborhood of, but close in the sense that it's diffeomorphic to the original zero set, the original sigma. Okay, so for this, you need something else, because in general it's not true that if you have two functions that are close in CK norm, any K that you want, the zero sets don't need to be close. You need some robustness, some structural stability of the set. Okay? And this is even more dramatic for dynamical systems when you study streamlines or vortex lines of solutions to fluid mechanics equations. So you need something that is called structural stability, that I'm going to introduce now, the definition. And it's something that is required directly from the problem, because you want to analyze the object, the zero set, for something that is close to another function whose zero set is controlled. So you need to control also the closeness, in some sense, of the zero set. Closeness in the sense of the existence of this diffusion. So you need robustness. So the nodal set we need. So for this strategy to be successful, we need that this n of u, or at least the component of n of u in the neighborhood, that n of u to be robust. Okay? Or I would say n of v. So this means be robust under small perturbations. So more precisely, if and this will be the definition of the structural stability. Structurally stable. Of this n of v being structurally stable. So if you have a function u that is close to b in the neighborhood, then this structural stability, what just means is that n of u has a component, a connected component in the neighborhood under consideration in n of sigma that is diffuse to sigma. Okay? And the diffuse being close to the delta. Being, say, delta close to the identity. Okay? This is a structural stability. So the nodal set of V is structurally stable if for any u, for any smooth function u, actually, for any u c infinity Rn close to V in the neighborhood, if for any u close to V in the neighborhood, the nodal set of u has a connected component in the neighborhood which is diffeomorphic to sigma, this diffeo being also delta close, you have continuity. This is a structural stability. And we want to construct, so in step 1, we will need to control, or we will need not only to construct the local solution with the zero set, not only that, but we need to control the structural stability of this zero set. We want both things, a local solution with a zero set, and this zero set being structurally stable. This makes things harder. Not here, this will be easy, because it's a direct application of the classical Thom's theorem, and actually it's essentially a consequence of, will be consequence of implicit function theorem here, but it's more dramatic in the case of fluid mechanics. There it will be, well, I'm not talking about fluid mechanics in this course, but if you want to develop this strategy to study vortex lines of solutions to Euler equation or Navier-Stokes equations, more technology will be required there, and it will be more sophisticated, much more, because it's not the level set of a function, it's the integral curves. The integral curves of an ODE, and integral curves of an ODE are much more unstable than the level set of a function. But that's another story. So, so in order to develop this strategy, now I'm going to introduce these two techniques. And actually, I'm finishing in 1 minute, or almost finished, right? Okay, so so just to start tomorrow, just I will start with Thom's theorem. Thom's theorem. It's sometimes called isotropy theorem. Isotropy theorem. It's a theorem that goes back to the 50s. I'll not prove it, although, well, I'll say something about idea of the proof. It's not very hard in this context. But just I'll use it. Okay, so simply I'll state the theorem in a simpler case that includes and this will be done tomorrow. And after this, I'll focus on the Runge type global approximation theorem for Helmholtz equation. I will give in full detail the proof. I don't know. In the GMA school, it took 2 hours. The proof of this. Here, I don't know. It depends on. Well, here maybe less because there will be some exercises that I will ask the students to do. So probably some computations. I will do some computations. Just to give the students who will do it. But at least tomorrow I will spend the whole time